Hello, this is David McMahon coming to you again with a section out of Unit 6. This time we're going to be talking about Section 6.2, Right Triangle Trigonometry Applications. So you can add that entry to your table of contents. Let's go ahead and get started with the notes. Now before you scramble to write everything down here, we're just trying to understand some things. Right triangle trigonometry specifically deals with similar triangles. So again, I've got that same set of triangles that we had from before. And with right triangle trigonometry, oftentimes we focus on one of the non-right angles, so one of the acute angles. And a lot of times we put a symbol in those angles. It looks like a circle with a line through it. It's called theta. Okay, so just some notation. That angle is pronounced theta. And it's like a variable, so we can put any number we want in place of this angle. What we're trying to show here is that all those acute angles are the same. And since those are right triangles, all those right triangles are similar. So right triangle trigonometry basically just use some proportional reasoning skills in order to determine missing side lengths, or in some cases, missing angles. We did some work with special triangles, and with right triangle trigonometry, I think something to write down here for sure is this idea that you can have any right triangle work with this. And we're going to be talking about something called a sine ratio, a cosine ratio, and a tangent ratio in this right triangle. So I want to label some things here. We're going to make sure that we label the one of the angles in the triangle is a 90-degree angle, and then we're going to make sure that we designate one of the two acute angles as our, I guess, desired angle, theta. Now what we can do is mark off the sides. So in any right triangle, and this is any right triangle, the side across from the right angle is called the hypotenuse. And the side that's across from angle theta doesn't really have its own name, but a lot of people call it the opposite side. And I think it's a good idea to write opposite to theta. Let's see, it's across from theta, like that. And then the remaining side is next to theta. We use a different word. We say adjacent. So when you are dealing with these various ratios, we can have a sine ratio, a cosine ratio, and a tangent ratio. The sine ratio is actually equal to the length of the opposite side, the length of the side opposite to theta, divided by the length of the hypotenuse. So a lot of times we abbreviate this and we write opposite over hypotenuse. And then the cosine ratio is defined to be the length of the side adjacent to angle theta and divided by the length of the hypotenuse. And then the tangent ratio is oftentimes defined to be the side length opposite angle theta divided by the side length adjacent to angle theta. So you'll see this sometimes where they write opposite over adjacent, or OPP over ADJ. Now I know that some people, they really like this idea of an acronym. So they write something down like this. Where the three parts of that word SOHCAHTOA help people remember these three trigonometric ratios. So some people use this. I tend to actually set up proportional triangles, and I'm going to show you how to think about that, because I think it's helpful to have more than one way to do these. Before we do any of that, though, I think it's time to just set your pencil down for a second, and we need to talk about unit right triangles. And unit right triangles are triangles that have one of the side lengths is 1. So when we are developing trigonometry, a lot of times we talk about things being in a unit circle. So this hypotenuse becomes 1. And then we try and figure out what the other two side lengths are. What I hope you notice in this diagram that's spinning around right now is that there's a blue triangle inside there. See how it kind of flips over and then it moves over to the other quadrant? When it's in this first quadrant, and let's be super clear here, this is called quadrant number 1. Okay, when it's in the first quadrant, then the horizontal component and the vertical component are both positive. Okay, so that kind of matches what we have in this triangle over here, where we would have an angle, theta, and I think in this diagram they're using the angle alpha, that looks like this. So that's called alpha. But all we're doing here is just noting that that particular triangle comes from looking at various triangles in a circle. So this is a unit circle. It's a circle of radius 1. And then we're just looking at triangles that fit inside that circle. That's all. Okay, that's right triangle trigonometry. And we're going to try and kind of show you how to use right triangle trigonometry now. We were talking about those various measurements, and what I noticed, I like this one, go slower. The blue length that is marked cos or cos, or that's cosine. Okay, so I see that that length is biggest in the positive direction when the angle is tiny. Okay, the angle of this triangle in the first quadrant is really teeny tiny. And then cosine gets to be small as the angle gets closer to 90 degrees. So, and then just so we can all understand here, what I'm talking about is this rotation. Okay, so that rotation is 90 degrees, and that's when the red line that's marked SIN, that's sine, the sine ratio, that's as big as it's ever going to get. It's equal to 1. Okay. And then the sine ratio gets smaller, and then it gets negative. The biggest it's ever going to get in the negative direction is 1 unit, because this is a unit circle. This is a circle of radius 1. Okay, so sine of an angle and cosine of an angle are kind of trapped in between -1 and +1. The biggest cosine of an angle is ever going to get is +1, and the smallest it's ever going to get is -1. Okay, so and they're just numbers. They're lengths on this diagram. So when we say cosine of 19 degrees, you'd have to draw in a 19-degree triangle and then figure out what that horizontal length is. When we say sine of 73 degrees, you draw in a triangle that had a 73-degree angle and then figure out what that vertical height would be. I noticed that there's also something called tangent on here. And tangent is this length tangent to the outside of the circle. That's kind of where the name comes from. And really, that tangent ratio is opposite over adjacent. It's the rise over the run. It's the slope of the radius of the circle. Okay, so, but then numerically, because of the way similar triangles work, it also works out to be the this length on a tangent outside. Okay, so I thought that would be helpful to see that before we really get rolling. As you move forward in mathematics, you're going to be graphing these trigonometric ratios as functions. So what I hope you see in the green circle there is just this, the red length in particular. Notice that red point. Okay, so I'll try and follow it around. That red point is just the vertical height of the dot going around the circle. Okay. And it's just mapping this out. And the biggest it ever gets is to be +1, and the smallest it ever gets to be is -1. And it just goes up and down, up and down. And then the blue curve is a little bit more complicated. It's measuring the horizontal distance, okay, and it's kind of bouncing back and forth along here between -1 and +1. And then they're using a translation to move it up to a curve and be able to go kind of up and down on a y-axis. Okay, so we're going to be eventually graphing functions. I don't think we're going to get to that this year, but we're graphing. We're going to be talking about the graphs of those trigonometric ratios. So they're just waves, trigonometric waves. Okay, so this is a static picture of sine of x. I mean, it's just, I hope you can see, it's just a wave that the biggest that sine of x ever gets is when x is, the angle is 90 degrees, or the input is 90 degrees, and then the output would be 1. And then if the input is 270 degrees, the output would be -1. So we just kind of go bounce up and down. Let's set all that aside. Okay, and let's talk about unit right triangles. I just want to show you this. So we said before that, and you can write this down now, where we've got a unit right triangle, and we're going to have the hypotenuse equal to 1. That's super important. Because if the hypotenuse is 1, that means that the side across from the angle theta is actually equal to sine of the angle theta. You're like, wait a second, I thought the sine of theta was equal to the opposite side divided by the hypotenuse. Look, it is. Sine of theta equals this length divided by 1. So that opposite side is sine of theta. It's a length. Okay, it's going to be smaller than 1 because the biggest side on this right triangle is the hypotenuse. All the other two sides are smaller than 1. And then I bet you already guessed that the adjacent side here, or the side that's next to theta, the horizontal side, is actually equal to cosine of theta. So we can use this then to solve other triangles. And when I say solve, we can find missing side lengths on other triangles just by using this, this particular triangle. So I'm going to color that in blue. I'm going to group it together and possibly use this on another page. Oh, like this page. Here's some example problems. We'll be using that triangle that I had from before. Our unit triangle, let's make it a little bit smaller. And what we can do is compare this unit triangle with any one of these triangles. You see, I could make that blue triangle be just like any of these other triangles just by scrunching it down or stretching it out. But then the sine ratio and the cosine ratio they won't change. Okay, so I can make those pictures look the same. And then I can set up some proportions. Okay, so check this out. We can, and here's how I solve these problems. I draw in another triangle, and then I just label it. It's a 15-degree triangle. The hypotenuse is 1. The opposite side is sine of 15 degrees. The adjacent side is cosine of 15 degrees. And then I can set up a proportion. Okay, so my proportion in this case is going to be, let's see, in my first triangle, I want to figure out what x is, and the side that I know is 25. See that? I'm just looking at these two pieces. Then I just set up the same ratio in the other triangle. That's got to be equal to, let's see, x would match with cosine of 15, so I put that on top. And then 1 goes on the bottom. So now if I move my ugly mug out of the way here, I can maybe try and solve this equation. And I think we can do that in like almost one step. If I want to get x by itself, I just multiply both sides by 25. So x would be equal to 25 multiplied by cosine of 15 degrees. And I'm not even going to write divided by 1. Okay, and then I could type that into a calculator. I could even open another tab on my browser and type in 25 times cosine and then put the 15 in parentheses. Be willing to bet that it's going to return a value for you. And I got 24.1. Okay, so let's talk about some of these other problems. And here again, this is our, oh, these triangles don't look the same. Let's make them look the same. See, I can stretch this out and make these two triangles look the same, and that ratio between, the designation of the side lengths doesn't change. That's pretty neat. So if I'm going to try this, let's do this again. So we'll draw in our triangle. So this is a 64-degree angle. We've got the side length marked X, but then we know that this is going to be a unit triangle. The side across from 64 is sine of 64. The side next to 64 degrees or adjacent to 64 degrees is cosine of 64. And I can quickly set up a ratio here. I want to know x, okay? So I'm going to write x divided by a side I know, x divided by 21. I don't even pay attention to like where they are. I'm going to put x on top every time. Okay? X divided by 21 is equal to, in the other triangle, x matches up with sine of 64. And then 21 matches up with the side length. It's a hypotenuse 1. So now I can solve that problem. Now that's a proportion. I can multiply both sides of that equation by 21 and get x equals 21 multiplied by sine of 64 degrees. And that one I got 18.9. And a good thing to do after you get done, you got a solution, go look at the original picture. 18.9. If I wrote x equals 18.9 right here, would it make sense? Okay. I know for sure that that side better be shorter than 21, because 21 is the longest side in that triangle. Okay, so if I came up with an answer that was bigger than 21, I know I did something wrong. Okay, and then I could go back and see if I put sine of 64 in the right spot. Okay, and if you were gonna, we'll just get this one set up for you. So in this case, we would draw in another triangle. It's a 22-degree right triangle. So we've got a sine of 22, a cosine of 22, and a 1. Oh, we might have to go through and do this one. Let's see. So if I'm going to set this up, x over 29 would have to be equal to, let's see, x matches up with sine of 22. And then 29 matches up with cosine. Oh boy, we've got to have 2 of them there. And that's okay. That's perfectly fine to have 2 of those ratios there. You can do that. 2 of those trigonometric ratios, and then we're going to, let's block this off and give myself just a little extra room. In this case, we would have x is equal to 29 multiplied by sine of 22 divided by cosine of 22, both degrees. So then x would be equal to 11.7. Now, we have that third ratio, tangent. Tangent is defined to be the opposite side length divided by the adjacent side length in any right triangle. What I have written here in pink is tangent of 22 degrees. Okay, so you might actually see this set up sometimes where they rewrite this and they'd say x over 29 is equal to tangent of 22. And you can check it out on your calculator. sine of 22 degrees divided by cosine of 22 degrees is the same as tangent of 22 degrees. Okay, so that's another way of tackling that problem. 29 multiplied by tangent of 22 degrees is 11.7, or really close. Let's take a look at a couple of other problems. I got to get myself out of the way again. Okay, now all of these problems, I've got these set up in such a way. Let's take a look at number 5, and I'll leave the others for you. In number 5, I think we do our same strategy. Draw in our triangle. It's a 45-degree right triangle. So we've got a 24 here, and we've got an x here. Oh, whoopsie daisy. The hypotenuse is 1, and the adjacent side is cosine of 45 degrees, and the opposite side is sine of 45 degrees. Then we'd set up our trigonometric ratio like we did before, set up a proportion. So x over 24 in the original triangle would be equal to, now I got to be careful, x matches with 1. 1 on top, cosine of 45 degrees on the bottom. Now, I think some people are going to try and tell you that you'd have to set this up as cosine of 45 degrees is equal to the opposite side, or the adjacent side, divided by the hypotenuse. So you'd have a fraction that said 24 over x. And I find that students make a lot of mistakes when they put an x in the denominator. So I always write it this way. I'd say x over 24, and then figure out which fraction I'm going to write in the other triangle. And the real advantage here is that now my answer is just x equals 24 times 1. That's easy to do. Divided by cosine of 45 degrees. Also easy to do. Okay, so I can just type that into a calculator just like I see it, and I get an answer. So in this case, x is 33.9, which, if you were really clever and you remembered our lesson from 6.1, you would know that 33.9 is a good approximation of 24 root 2, because this is a 45, 45, 90 triangle, so x has to be 24 times the square root of 2. See, trigonometry and special right triangles, they actually go together. Okay, so you could solve the other couple of problems there. I do want to talk briefly about some applications. So in these applications, a lot of times what we wind up having to do is understand and interpret a situation. So in this case, we've got this tall tree in a park. It says there's a certain point on the ground that is 40 meters from the base of the tree, and the angle between the ground and the line of sight from the point on the ground to the top of the tree is 35 degrees. So we're going to draw just a sketch of a picture. Okay, so I'm going to have a tree. And then along the ground here, this is 40 meters. And then the angle to the top of the tree, I think my tree is a little tall. The angle to the top of the tree is 35 degrees. And then it says, calculate the approximate height of the tree. There, I have a diagram. That diagram represents the situation described above. And now I can use right triangle trigonometry to find that value of x. Let's look at another application. A ladder that's 20 feet long is leaning against the side of a building. So if the angle formed between the ladder and the ground is 75 degrees, how far is the bottom of the ladder from the base of the building? So we'll draw another triangle picture. Okay, so we've got a building. We've got a ladder leaning against the building. And let's see, it says the angle formed between the ladder and the ground is 75 degrees. And it tells us the ladder is 20 feet long. How far is the bottom of the ladder from the base of the building? Here's the bottom of the ladder. Here's the base of the building. That far. This is a right angle, by the way. That's another picture where you could find that length x using some trigonometric ratios like we practiced before. Last one. At the entrance of a building, same building maybe, there's a ramp for wheelchair access. The length of the ramp is 9 meters. The angle between the horizontal ground and the angled ramp is 5 degrees. Draw a picture of this situation. Okay. So we've got a ramp going up, and you can add to your ramp if you like. But it says this angle is 5 degrees. Kind of hard to draw a 5-degree angle there. And the ramp is 9 meters long. Determine the height of the tall end of the ramp. That's this over here. So you could use some trigonometry to figure out the height of that tall end of the ramp. Okay, we got a lot to chew on there. I hope that this helps you understand trigonometry just a smidge more. I know that you've looked at it last year, so hopefully some of this is some review. I do know that some of you are going to continue to use the SOHCAHTOA acronym to set up your trigonometric ratios, but I do challenge you to kind of really think long and hard about that you can always set up a unit triangle pretty quickly. And then it's easy to set up a equation. So x over 9 is one ratio, and then the corresponding ratio would be sine of 5 degrees over 1. That equation's easy peasy to solve. Okay. Hope you have a great afternoon.